Daniel, can you hear me and see the screen? Can you hear me? Somehow I can't hear you.
Hello, can you hear me now?
Yeah. So you can hear me and see the screen?
Yes, I can hear you.
Okay, thank you.
Yeah, no problem.
Good morning.
Good morning.
I'm going to continue our discussion of quantum mechanics that we introduced last time. So this slide essentially captures the essential principles of quantum mechanics that we'll be using. We said that everything in nature has a wave-particle duality, and depending on the experiments that you do, either the particle aspect or the wave aspect shows up. In terms of the wave aspect, everything in quantum mechanics is described by a complex function, psi, which is a function of position r, x, y, z, and time, where the psi is known as the wave function. It's a complex quantity, it has a real and an imaginary part. And just as for a classical wave with an amplitude A, we saw that amplitude squared gives you the intensity or the power of the wave. Similarly, in quantum mechanics, psi magnitude square or psi star psi, as shown over here, gives you the probability density of finding a particle between, say, locations x and x plus dx, y plus dy, and z plus dz, okay, at that instant in time. The wave function in general would be evolving as a function of time. Now, if psi magnitude square is interpreted as the probability density function, obviously, if we integrate that probability density from minus to plus infinity over the entire universe, the particle has to be somewhere. Therefore, all those probability densities have to add up to 1, and that property of the wave function is known as the normalization of the wave function. Now, sometimes when you do calculations, you might find that it doesn't add up to 1, integrate to 1. Not a problem at all. It just means that you have a scaling problem, okay? So if it integrates to, say, a, you just divide the wave function by 1 over square root of a, so that once you square it, the a's cancel out, okay? Now, this interpretation of the wave function as being the probability density immediately tells you what some of the mathematical properties of a wave function should be. So for example, if I plot the wave function as a function of position x, let's just look at a one-dimensional problem. First of all, it has to be normalized. We've already seen that. Now, let me ask you, do you think you could have a wave function which looks like this, which is multi-valued between, say, location x1 and x2? You think that's a physically valid wave function? Anybody? If it's multi-valued, what I'm saying is between x1 and x2, those positions, the particle has a probability given by the square of that or the square of that, right? So you have two probabilities. Is that feasible physically?
No.
No. So a valid wave function cannot be multi-valued, okay? Similarly, just keeping at the back of your mind the principle that psi magnitude squared means a probability density, you can kind of infer what some of the mathematical properties of a valid wave function should be, okay? And such properties, mathematical properties, are described by saying that the wave function is well behaved, okay? Not well behaved as in Trump supporters, but well behaved mathematically, okay? All right, so next principle of quantum mechanics is for every classical quantity, if you went to the lab and did a measurement of, say, the position of a particle or momentum or energy, the corresponding quantum mechanical operators. Now, for position, it's in quantum mechanics, it's also R, or if it's a one-dimensional problem, it would be X. And then we said that if you have some spatially varying potential energy, V of X, in quantum mechanics, that would also be written as V of X. Momentum, on the other hand, is given by h bar, which is h over 2 pi, divided by j being the imaginary number, square root of -1. Sometimes it's also written as I try to be consistent, but I sometimes flip-flop, times the grad function. So the grad function in 3D would be unit vector along the x-axis, del x, unit vector along y-axis, del y, and then unit vector along z, del z, okay? In our class, we'll look at a simpler case of one-dimensional problems only. So this potential function would be h bar over j del x along that axis, okay? And then finally, the energy is given by minus h bar over j del t, okay? Now, if you take a formal course in quantum mechanics, they'll introduce an energy term in a slightly different fashion, but ultimately you get the same result. And this is a simplified description of quantum mechanics that's perfectly adequate for our purposes, okay? And then the final principle is if you do an experiment on some macroscopic object, say made up of billions of electrons, if you will, you're going to think of each electron as a distinct quantum mechanical system. So when you do a measurement on a macroscopic object, you'd get some average result for all these electrons. This is called an ensemble of electrons, okay? Each electron may give you slightly different eigenvalues, but then for this entire ensemble, you'd get an average value, which I indicate as Q within angular brackets, given by this integral over here. So you take this overall wave function, which we said last time could be written as a linear combination of individual eigenfunctions with different amplitudes, C1, C2, C3, etc. Then whatever physical quantity I'm interested in, I construct its corresponding operator. You operate on the wave function by a Q operator. It's not a multiplication, it's a operation. So for example, del t means I take the time derivative, or del square del x square means I take the second derivative with respect to position, and so on and so forth. Okay. And whatever result you get by doing that mathematical operation, you then multiply by the complex conjugate of psi, and then you simply integrate from minus to plus infinity. Okay. Because the particle has different probability densities to be at different locations. And if the wave function was normalized, that's all that you need. You just need the numerator. Now, if the wave function wasn't normalized, you divide by this denominator, because that basically gives you the scaling factor. So it's really quite straightforward. Quantum mechanics, people who haven't taken a course think that, gosh, it's very, very difficult. As I said, the mathematics is actually simpler than what you have in Maxwell's EMAG. Okay. The problem with quantum mechanics is not so much the math, it's the physical interpretation, because we live in a macroscopic world. So sometimes the physics of quantum mechanics seems to be counterintuitive. So that's the confusing part. Okay. All right. So now with that recipe for solving problems in quantum mechanics, we can then derive the key equation in quantum mechanics, the famous Schrodinger equation, which is operating on a wave function by a so-called Hamiltonian operator, which is the sum total of the kinetic plus potential energy operators, T plus V. You should get the total energy operating on the wave function. Okay. Interestingly, if you read the history of physics, this guy Hamilton lived in the middle of the 19th century. He was a British mathematician. So obviously he knew nothing about quantum mechanics, but the mathematics that he had derived for classical mechanics turned out to be useful for quantum mechanics also. Okay. Now, I know our recipe for writing down quantum mechanical operators. So for the kinetic energy, that's of course half mv squared, or equivalently, you can write that as p squared over 2m, p being the momentum. Okay, and we know what the recipe for momentum is. So that would be h bar over j del x. Now, if I take p squared, that becomes h bar squared j squared, which gives you -1, divided by 2m. Okay. So that's my kinetic energy operator. And then finally, del x, it's not del psi del x squared, but it's del square psi del x squared. So that's a key point. Okay. So what that means is I differentiate the wave function with respect to position, and then I differentiate the result once more. I take the second derivative. Okay. So that's the only thing that you have to be careful about. Okay. So that's my kinetic energy operator. Okay. So that gives you the first term over here. So it's minus h bar, minus because I take j squared divided by 2m, and second derivative with respect to position of the wave function. That's the kinetic energy term. The potential energy term, v, is a function of x. So whatever function I have in my problem statement. And as I said, x corresponds to x in quantum mechanics also. So it's straightforward. You simply multiply the wave function by v of x. Then that gives you the total energy. Kinetic plus potential energy gives you the total energy. And the operator for total energy is minus h bar over j del t. So now it's a time derivative. On the left-hand side, you had a spatial derivative, second derivative. On the right-hand side, you have a time derivative. Okay. Now this, of course, is a partial differential equation. And the way we solved it is by a standard trick in partial differential equations known as a separation of variables. And the essence of that idea is if I have some function psi, which is a function of x and t, you attempt a solution as psi of x alone times a function phi of time alone. Okay. Now, in some cases, you may not be able to separate them nicely into two product terms like this. Okay. But it just so happens that in this particular case, it works out very nicely. I'm not going to repeat all that math again, but basically what you do is wherever I have psi of xt, you write it as psi of x times phi of t in each of these terms in the Schrodinger equation. And then I divide every term by 1 divided by psi of x times phi of t. Okay. Now note this psi of x is just a spatial part, and don't confuse that with the overall psi xt. And I indicate that with a slightly different symbol for psi. So this overall psi wave function is a function both of x and time, while this psi of x is just the spatially dependent part of it. Okay. Now, hopefully, you try to work out this, on your own. Just convince yourself that I wasn't lying. So if you divide each term by psi of x times phi of t, for the first term, you'll find that the phi of t term cancels out. Why? Well, the phi of t is not a function of position. So you could pull that out of this derivative, and then that cancels with the phi of t, right? But I then, for the first term, I'd end up with 1 over psi of x, and then everything that I have over here, okay? For the second term, everything cancels out, right? Because I'm dividing by psi of x, phi of t, so both of these terms cancel out. On the other hand, on the right-hand side, if I have psi of x, phi of t, del t of that, the psi of x is independent of time. So it's kind of like a constant. So you can bring it to the left-hand side of the time derivative. And then when I divide by psi of x, phi of t, the psi of x is canceled out. So what I'm left on the right-hand side is 1 over phi t del t, okay? While on the left-hand side, you'd find I have 1 over psi x, her square over 2m, del square psi del x square, and then v of x, okay? So what I have is something very interesting. On the left-hand side, I have a function of x alone. There's no time dependency. On the right-hand side, I have a function of time alone. There's no x dependency. And if you have some arbitrary function of x, which equals to some function of time, the only way that's possible is if each of those is equal to constant. And I call that constant E, because I know what the answer is. That'll turn out to be the separation constant, turns out to be the energy of the system, the so-called eigenenergy, okay? So if you write both sides equal to E, the time-dependent part is trivial to solve. It's a simple first-order ordinary differential equation shown over here. And the solution of that is an exponential function, e to the power minus j E divided by h bar times time, okay? And I can already see the Planck expression popping out of it, because we know that E over h bar is omega. So this wave function rotates as a function of time with an angular frequency of omega radians per second, okay? And that's true for all wave functions. So the time-dependent part for these eigenfunctions will have this nice variation in time depending on the eigenenergies. The difference from one quantum mechanical problem to the other comes from the spatially dependent part, because, as I told you, you can specify different v of x's. That's really the only difference from one quantum mechanical problem to the other, okay? So turning to the left-hand side, that's the spatially dependent part of the differential equation. I end up getting this. So what I get is the second derivative, d2 psi dx squared plus v of x psi equal to the separation constant E, which will turn to be the total energy times psi. And this, as you said, is a so-called eigenvalue equation, because you remember from your differential equations or linear algebra that if you operate on a function, and the left-hand side, of course, have operators, right? It's a composite operator involving a second derivative plus this v of x. So that operator operating on psi of x, if it gives me a constant times the same function back again, those are called eigenvalue equations. And the solutions for those functions are called eigenfunctions. And these corresponding constants are known as eigenvalues, okay? So what it tells you is I have certain nice solutions where operating on that function gives you back the same shape of the function times a constant, okay? Now, once I get those eigenfunctions, I denote those as psi n for different values n, and these are sort of indices indicating the different eigenvalues. So n would range from, say, 1, 2, 3, with different constants C1, kind of giving you the different amplitudes of the different wave functions, okay? So a general wave function may not be a single eigenfunction. It might be a linear combination of eigenfunctions, okay? And the analogy that we used was, you can think of these eigenfunctions, these psi n terms, as the analog of these unit vectors x, y, z in Euclidean space, okay? And just as any vector v can be written as a decomposition of v, I wrote it last time. So any vector b, say, and I choose b because I've reserved v for potential energy in this case. I don't want to confuse you. So some vector b, say the Banerjee vector, can be written as components along the x, y, z axis, bx, by, bz, times the corresponding unit vectors x, y, z, right? So these unit vectors x, y, z are the analog of your eigenfunctions, and these bx, by, bz are the amplitude amplitudes of this corresponding eigenfunctions. Okay, so then when I have some general function solution, general wave function psi, that psi is written in terms of these linear combinations of these eigenfunctions. And basically, when I calculate an average quantity like this, what I'm doing is I'll get some eigenvalue, say E1, multiplied by C1 squared. That's the amplitude of that eigenfunction, plus E2 times C2 squared, C3, and so on and so forth. Okay, so that's how these calculations work out in quantum mechanics. Now, in our class, I won't ask you to do complicated solutions involving a series of summation of eigenfunctions like this. We just consider the simple case of single eigenstates and eigenvalues. Okay, everybody with me so far? All right, so now we have this master equation that I want to solve, and this sometimes is known as the time-independent Schrodinger equation, as opposed to the starting Schrodinger equation, which of course has a time-dependent part to it. Okay. All right. So what we started doing was we take this time-independent Schrodinger equation and solve it for a few choices of v of x. So you can think of this as worked out examples of the solution of the Schrodinger equation. Okay. Now, what's the simplest choice of v of x? Clearly, the simplest possible v of x would be choose that to be a constant. So have the same constant potential energy everywhere. Now, in classical physics, if the particle moved in a region with constant potential energy, you may remember that the force is given by minus d potential energy dx. Okay, that means it doesn't see any force. Okay, if you think of, say, potential energy as the gravitational potential energy, it's like having a particle roll around on a flat surface. Okay, so there's no variation of the gravitational potential energy on a flat surface. So it'll roll around freely. It's a force-free particle. It's a free particle, right? Same thing over here. So if v of x is a constant, it's basically no forces. It's a free particle. Okay. You may also recall that potential energy is not an absolute quantity. You have to choose a suitable reference. And since it's a constant, to make my life easier, I might as well choose that reference to match with that potential energy. So I can set that equal to 0. Okay. So for the first solution, this middle term, v of x, vanishes. Okay. And I'm left with a simpler equation that I have to solve. Okay. And that's what we solved in the last class. I know these things are getting a little bit messy. So what I have to do is the second derivative with respect to x, d2 psi dx squared minus h bar squared over 2m. I multiply through every term by 2m over h bar squared. So for the first term, I simply get the second derivative. And on the right-hand side, I will end up with 2m e divided by h bar squared. Okay. And since I have a minus sign, I bring it over. So I end up with this differential equation. Okay. So it's second derivative of psi with respect to x squared plus 2me over h bar squared times psi equal to 0, where I now introduce a new term, k squared, and I call that 2me over h bar squared. See what I've done? Now that k that I introduce will turn out to be the wave vector, which is 2 pi over lambda. Okay, and I'm choosing this because I know the final answer, so might as well choose the right symbols to begin with, rather than use a different symbol, work it out, and see, this is the wave vector, so change the symbols at that point. Okay, I'm looking ahead. All right, so what is the solution of this second order differential equation? Well, you can write that either as a linear combination of a term e to the power I j kx, some constant, plus e to the power minus j kx, okay, with another constant, say a and b, okay? Or using the Euler relationship, we know that e to the power j kx it can be written in terms of sine kx plus cosine kx with different terms, say a prime plus b prime. So depending on the problem at hand, I can write down the solution either in terms of these exponentials or sine and cosines. Okay, you can go back and forth between one and the other. And it so happens that in the case of a free particle, where the particle can propagate freely between minus and plus infinity, it's easier to write it in terms of these exponential functions. Okay, and if you do that, so I get a solution a being the amplitude, so that's your normalization term. e to the power j kx. That's the spatially dependent part. And then from the time dependent solution, I have to plug in the time dependency, which is the same everywhere, right? It's e to the power minus j omega t. So if I choose a solution e to the power plus j kx, you multiply that by the time dependency, which is e to the power minus j omega t, okay? And this, you may remember from your physics classes or circuits and systems, this is nothing but a plane wave propagating along the plus x-axis, okay? You'll also get another solution, e to the power minus jkx. When I solve this differential equation, that will be a plane wave propagating along the minus x-axis, okay? And you can then choose linear combinations of the two, all right? Let's just assume, just to make our life simple, let's just consider the positive propagating wave and see what we can do with it. So next, what I wanted to do was to calculate these expectation values of momentum. This is a one-dimensional problem, so let's just look at P of x and energy, okay? Now, what is the recipe? Well, I know what the recipe is from my quantum mechanical dictionary. Whatever the wave function is, I have to operate by the corresponding operator, and the result is multiplied by the complex conjugate. And if the wave function wasn't normalized, you divide by the denominator over here, right? So for momentum, the operator is minus, sorry, not minus, h bar over j del x, right? So I have to differentiate this wave function, e to the power j kx, with respect to x, okay? Now, what do I get if I differentiate an exponential? I love exponentials because if you differentiate an exponential, you get back the exponential times this exponent jkx. If you integrate an exponential, you get an exponential times 1 over whatever you have in the exponent. Now, luckily, in our class, we'll be integrating and differentiating exponentials of different types all the time. And I love those, I mean, even I can integrate and differentiate exponential functions, okay? So if I differentiate this, what will pop out is j kx, and I'll be left with the exponential, okay? And then remember, I have to multiply with the complex conjugate. So that gives you e to the power minus jkx. Therefore, the exponentials will cancel out. And what I'll be left with is a star a, or a magnitude square, okay, times kx, jkx, and the j cancels out, and I'll be left with h bar kx, okay? But I face a problem because then if I integrate from minus to plus infinity, what I'm integrating is a constant, a squared h bar kx, and that gives you infinity. The integral blows up, okay? So remember, of course, that you have to divide by this term in the denominator to make sure that everything is scaling properly, okay? The wave functions are normalized. Well, in the denominator, unfortunately, psi star psi gives you this, the exponentials cancel out, and I'm integrating a constant, which is a magnitude square from minus to plus infinity. That also blows up. So I got this funny situation that I can integral in the numerator, which is infinity, divided by something in the denominator, which is also infinity, right? So I don't know what the heck that gives me. So the trick for this is you don't integrate from minus to plus infinity from the get-go. You first integrate within a finite region, minus L to L, both in the numerator and the denominator. And you'd find then that the L's cancel out nicely, okay? And then you pretend that after the L's have canceled out, I take the limits of L going to infinity, okay? So sometimes you have to play this trick where you don't integrate from minus to plus infinity from the start. You integrate within a finite volume, and you'll find that that finite volume terms will cancel out, and then you pretend that that volume is extended to infinity, okay? So this first expression is a very nice expression because it tells you that the momentum works out to h bar kx, where of course we saw in the last class, kx is your de Broglie, is given by 2 pi over the de Broglie wavelength, okay? So this is nothing but your de Broglie relationship. The momentum is equal to h bar times the wave vector kx, where kx turns out to be h over lambda. Similarly, if you did it for energy, now you have to take the time derivative, and you should do the math on your own to convince yourself. That works out to h bar omega. Or you could also write it as, h over 2 pi times nu. So omega is frequency in radians per second, or nu is frequency in hertz. Okay? And that, of course, is the Planck relationship. And this, of course, captures the essence of wave-particle duality in both of these expressions, because things like wavelength and frequency have connotations of waves, while quantities like momentum and energy have a connotation of particles, right? And like I said, these two relationships are going to be true every time for electrons, protons, neutrons, Banerjees, photons, whatever. Okay. However, you can also try to sometimes derive relationships between expressions in equation one, such as momentum, and quantities in equation two, such as energy. Those relationships are not universal. And what we wrote down last time was an expression between energy and momentum for, say, electrons. Now, for electrons, of course, we know if it's a free particle, we're looking at the free particle. The total energy is just the kinetic energy, which is p squared over 2m. P is h bar k. So I can then get h bar squared k squared over 2m. So now if I plot energy as a function of k, that's the equation of a parabola. So I get a parabolic relationship. That's going to be called a band structure, or the dispersion relationship for electrons. Now, how about for photons? How would I calculate the dispersion relationship for photons? Well, for photons, remember, we have the wavelength of a photon, nu, lambda, times its frequency, nu, equal to a constant, the speed of light, right? Now, I'm not going to go through every single step, but the wavelength is going to be proportional to 1 over k. So the first term will be basically proportional to 1 over momentum, okay? And the second term is proportional to frequency. Nu is, omega is 2 pi times frequency, okay? Now, now omega is then also going to be proportional to energy. So these are just proportionality constants now, okay? So if I was to plot energy as a function of momentum p for a photon, I end up getting energy will be proportional to c, which is a constant, the speed of light, times p. You guys with me? So you start from wavelength times frequency is a constant. Frequency is proportional to energy, and wavelength is proportional to 1 over k, wave vector k, or 1 over momentum. So now if I plot the dispersion relationship for photons, I don't get a parabolic relationship. I'll get straight lines whose slope is going to be proportional to c. It's not equal to c, but it's proportional to c, okay? So you get different dispersion relationships. That, by the way, also tells you why these are called dispersion relationships, because if you construct wave packets with different frequency components, you'd find that if it's dispersive, the different components would spread out at different frequencies. Hopefully you remember that from your circuits and systems classes. And the wave packet spreads out in time, or if it's a wave packet in space, it'll spread out in space. That's why it's called a dispersion relationship, okay? So for photons, you see that it doesn't disperse because it's all got the same velocity. Okay. All right. Let's work out one. Let's go to worked out example 2. This is a very important example because we'll be sort of invoking the results of this to explain other properties of semiconductors. Okay. So the second worked out example is the famous particle in a box problem. Okay, where I consider a particle shown by this red circle moving around in a potential profile which is constant between 0 and L. Okay, so up to this point, it's similar to the previous problem. Okay, where I chose a potential profile which was constant. But in the previous problem, the potential was constant everywhere. Now it's constant only between 0 and L. Then at 0, the potential energy goes up to infinity, and at L, it goes up to infinity. Okay, so it's infinity in these regions shown by these shaded red regions. Okay, so it's different in that sense. All right. So how do I solve it then? Well, as I said last time, at the end of the last class, you now have to use some physical intuition to determine what the appropriate boundary conditions are for your wave function. Okay, what do I mean by that? Well, if the potential energy is infinity in these red regions, what will be the total energy of this particle be in these red regions? Total energy is the sum total of kinetic plus potential. If the potential energy itself is infinity, the total energy has to be infinity, right? Can a particle have infinite energy in a physical problem? Obviously not. So what it says is the particle cannot appear in these red regions, okay? Now, if the particle cannot appear in those red regions, what is the probability density, psi squared, in those regions? has to be 0, right? So that then tells you my boundary conditions should be that the wave function evaluated at 0 should be 0, and the wave function evaluated at L should be equal to 0, right? So those are your boundary conditions. And that's a general principle that we'll observe, depending on the physical problem that I have in hand, you'll have different boundary conditions, which imposes conditions on the wave function, and that'll be key to solving it, all right? Now, other than the boundary condition, the rest of the solution between 0 and L is exactly the same as before. So this V of X can be set equal to 0 by choosing a suitable reference potential, okay? So now, once again, you can multiply throughout by 2m over h bar squared and bring everything over to one side. And what you'll end up getting then is the same equation as before, d2 psi dx squared plus k squared psi equal to 0, where k squared is your 2me over h bar squared, okay? All right. And the solution of that, of course, can be written as e to the power I kx, jkx plus e to the power minus jkx, or using the order relationship in terms of sine and cosine functions. So you can go back and forth, right? And in this particular case, it's easier to work in terms of sine and cosine functions, because now notice that the particle is not really a free particle, right? It's bounded within the box. So you create standing wave patterns as shown, for example, over here. The particle doesn't freely propagate from minus to plus infinity, okay? So I'll choose solutions in terms of sine and cosine functions, okay? So I'll write psi of x as some constant a sine kx plus another constant b cosine kx, okay? And you could have written the solutions in terms of exponential functions also, but it turns out to be easier in terms of writing it in terms of sines and cosines, okay? Now, once I have the solution, then I impose these boundary conditions, psi of 0 equal to 0 and psi of L equal to 0. Let's see what you get as a result. Let me write it a little bit more cleanly. So this is cosine, okay, times b. All right. So if I write down psi of 0, what should I get? I'll get a sine k times 0. What sine of 0 equal to? That's 0, right? So for sine of 0, I'll get psi of 0, I'll get a times 0 plus b times cosine 0. What's cosine 0 equal to? That's equal to 1, right? So that's my first boundary condition. Now, a times 0 gives you 0, of course. So what that tells you is b must be equal to 0, right? So I can drop the cosine term. I'm only left with the a sine kx. Now I use the second boundary condition. So I get psi of L, which is a sine kl, must be equal to 0. Now what does sine kl equal to 0 tell you? Kl must be equal to n, integer number, times pi, right? It can be 0, pi, 2 pi, and so on and so forth, right? So from this expression over here, k times L must be equal to n times pi, integer numbers n, or in other words, k should be n pi over L, okay? So then the solution psi of x becomes a times sine n pi x over L. Now, then I have to do the normalization of the wave function. I'm not going to do through the math. So you basically take psi magnitude squared, integrate from 0 to L, okay? You'll get sine squared times a squared. You set that equal to 1. And by setting it equal to 1, a will work up to root 2 over L. You should do that math on your own, just to convince yourself, okay? So root 2 over L is just your normalization function that makes sure that the integral of psi magnitude squared between 0 to L will give you 1, okay? Now you may say, why am I integrating between 0 to 1, L? Shouldn't I integrate from minus to plus infinity? Anybody have the answer?
Didn't we say no because of the fact that it would be infinity over infinity?
So you should integrate from minus to plus infinity, but remember, for x less than 0 or x greater than L, the wave function is 0, right? So that doesn't contribute. Okay, now once I have these values of K, I know what the energies would be because energy is given by h bar squared K squared. So that's now n squared pi squared over L squared divided by 2m. And that's this term over here. All right. Sorry, h bar squared. Yeah. Okay. Now, h bar is, of course, h over 2 pi. So here I'm writing it in terms of just h. And then if you get the 2 pi, the terms cancel out. So that's this expression over here. All right. Now let's graph out the solutions and see what the physics tells us. And that's really, really interesting. Okay. So the first solution, the first eigenstate will be for n equal to 1. If n equals 1, you'll get a wave function which is half of a sine function. So it's like a standing wave. So you can think of this wave function as like a string, which is fixed at the two ends of this infinite potential well. And if I plug the string, you can set up these vibrations, which are these half wave bobbing up and down. And corresponding to that, I get the first eigenenergy E1. Then for n equal to 2, I get a full sine function. Okay, so that's the next standing wave pattern, and so on and so forth. For this, I get the next energy, which is 4 times as large. The third eigenstate, it's 9 times as much as the first eigenenergy, and then that's corresponding wave function. Okay. Now, for a physical interpretation, what should I do to the wave function? If you take the square of that, right? Because that gives you the probability of finding the particle, this electron, say. Let's assume that this orange, this red thing was an electron. It could be anything. It could be something else also, but let's assume it's an electron because we are looking at the motion of electrons in a semiconductor in this class. So if I squared this, for the first eigenfunction, you get a lump in the middle and 0 at 0 and L. For the second one, it's interesting. So if you squared this, the positive lobe, of course, gives you a larger positive lobe. The 0 crossing gives you 0. And the negative part, if you square that, you get back a positive probability density, right? And this is very, very interesting. So what it tells you is, let's compare the distinction between the classical physics and quantum mechanics. So if this electron was described by classical physics, notice between 0 and L, it's a free particle essentially, right? So it'll travel with constant speed, hit this wall, bounce back, constant travel speed, constant speed, hit this wall, bounce back, and bounce back and forth if it had a certain kinetic energy, right? And then if I ask the question, what is the likelihood of finding the particle at different locations on a statistical basis, okay, on average? You keep doing this experiment and you take snapshots at different times. Clearly, it's bouncing back and forth. So if you observe it over a long time, the likelihood of finding the particle at any location between 0 and L would be the same, constant for a classical particle, right? But that's not the case for a quantum mechanical description. So what it tells you is in quantum mechanics, if the particle happened to be in the lowest energy state, E1, which is also sometimes called the ground state of the system, the lowest energy state, you're likely to find the particle most of the time in the middle of the well, less likely in these locations, and of course, 0 likelihood of finding it at 0 and L or outside of the box, okay? Let's look at the second eigenstate. Suppose it had a higher energy E2. It's likely to be found in this part of the well or that part of the well, but it's not likely to be found in the middle. And that's really, really weird, right? Because, how can the particle be appearing on the left-hand side and the right-hand side without having any probability of appearing in the middle, right? So that's, the weirdness of quantum mechanics starting to show up, okay? So what it's telling you is, if I measured the location of the particle of a single electron, most of the time I'd find it over here, less probability of finding it in a different experiment over here, lower likelihood of finding it here, 0 likelihood of finding it right in the middle or at 0 and L, then a very high likelihood of finding it here, and so on and so forth, okay? So the energy is quantized in terms of this quantum number, and you have corresponding wave functions, eigenfunctions. Now, in general, you could write down a wave function, which could be a linear combination of these eigenfunctions. Okay, so you can have some constant C1 times psi1 plus another constant C2 times psi2, and so on and so forth. And then when you do the measurement, you could get a value, an average value, which would be some weighted average of C1 squared times E1 plus C2 squared times E2, and so on and so forth, okay? But that would be the average if you did this quantum mechanical experiment many, many times. For a single measurement of the energy, you could either get E1 with a probability of C1 squared, or E2 with a probability of C2 squared, or E3 with a probability of C3 squared, and so on and so forth, okay? And that's the weird aspect of quantum mechanics. You know, you can't tell with absolute precision what value you would get in a particular quantum mechanical experiment. The best you can do is some probabilistic description of the experiment, right? I mean, I have a certain probability of, say, E1, a different probability of E2, and so on and so forth. And Einstein never liked that aspect of quantum mechanics. You know, he famously said that, you know, God does not play dice. Okay, I mean, so his stance was, you know, if you knew the exact, precise initial and boundary conditions of a problem in physics, you ought to be able to predict things precisely. And he never liked this business of, you know, I have different probabilities of getting different measurements. Okay, but you know, interestingly enough, all experiments that people have done can be explained by this mathematical formulation. Okay, and I mean, you can argue with the philosophical meaning of it, but the math works out beautifully. And you know, that's what you use to design transistors and lasers and all these other fancy things. Okay, so I wanted to study this particle in a box problem because we'll, you know, kind of invoke the results of this constantly in this course. Any questions on this? All right. Once I have that particle in a box problem under my belt, I'm going to solve two other problems, okay? But I won't solve these in as much detail as the first two. I'll just qualitatively give you a solution, and new physics will pop out. So the next problem is, I choose a v of x, which is once again constant between, say, x equal to 0 and x equal to L. At x equal to 0, it goes up to infinity, as in the previous particle in a infinite potential box problem. That part is still the same. But now the difference is, at x equal to L, it goes up not to infinity, but some finite value v naught. It stays at v naught between L and L plus W, and then goes back to 0 again. And now I put a particle, say in this red circle, in the box with an energy of that much. And I want to see what classical physics and quantum mechanics predicts, okay? Now, if the particle had an energy of that much, classically, what would that particle do? Well, it would go with a constant speed, hit this wall. Since the total energy is less than the potential barrier, it would bounce back. Here, of course, it's infinite potential barrier, bounce back and keep bouncing back and forth. On the other hand, if the particle had an energy like this, if it was moving like so, it would hit that wall and bounce back. But on this side, it would escape out of the well because it's a finite well right now, right? Quantum mechanics, however, tells us something very, very different, okay? So quantum mechanically, if I put in a wave function and I solve the Schrodinger equation, what is my recipe? Well, this complicated shape of v of x is what I'll put into the Schrodinger equation, right? Well, actually, the time independent part, okay, v of x, and just crank the machinery, right? You can solve it in a second on any laptop or computer, okay? Well, we won't do that. We just want to see what the solution might look like. All right, so if I solve for this v of x, as shown over here, what do you think would be the value of the wave function at 0, based on the same kind of physical intuition as before? Remember, at x equal to 0, the potential energy goes up to infinity. Therefore, psi of 0 must be equal to
0.
Very good. So the probability density has to go to 0. But now comes the catch. What is the wave function and wave function square of the probability density going to be at x equal to L, or between L and L plus W? Now the potential energy isn't infinity, it's some finite quantity. Is there any reason why the wave function should vanish under those conditions, quantum mechanically? No. You know, we have to actually put it in, solve the differential equation, okay? And that's what I'm qualitatively sketching over here for the psi square, the probability density. The probability density doesn't vanish within the well. And in fact, if you solve it, depending on the magnitude, the height of the well and the width of the well, it might have a non-zero value outside of the well, okay? Even if I solve it for an energy of the electron with the energy less than V naught. And that's a very weird result. So what it's telling you is electron with the total energy E is, of course, the sum total of the kinetic energy plus the potential energy. So for electron that I've chosen with the total energy less than V naught, even then, it can magically go through the barrier, and that process is called tunneling. So it doesn't go over the barrier, it's leaking through, the wave function is leaking through, and therefore there's a probability density leaking through the barrier. It tunnels or burrows through the barrier, okay? And that's something that, you cannot explain based on classical physics. And if you stop to think about it, it's really weird condition, right? Because if I've chosen a total energy E less than V naught, that's what I've done, right? I've chosen a particle that is normally going to be a bound particle classically, okay? So I've chosen a total energy E less than V naught. So for that particle to appear in the shaded region, what must be the sign of the kinetic energy? Kinetic energy is E minus V naught, right? So if I choose E less than V naught, what would be the sign of the kinetic energy for a particle which is in this region? Positive or negative?
Negative.
Negative. Now, kinetic energy, of course, is given by P squared over 2m, right? In classical physics, can that be a negative quantity?
No.
So that's something very, very strange, right? So this kinetic energy, P squared over 2m or h bar squared k squared over 2m is a negative quantity, it's less than 0. And the only way that's possible is if k is not a real wave vector anymore, but some imaginary wave vector e to the power I kappa, say, okay? So then if I have a wave function which previously we had called e to the power I kx, if k itself is an imaginary number, sorry, j times kappa, what will I get? You'll get e to the power, I keep slipping, j, now j kappa x. Now what's j squared equal to? -1. So you get e to the power minus kappa times x. In other words, the wave function dies down exponentially to some value, okay? And then you take the square of that, that's also an exponential. So what it tells you is, if this barrier is very, very wide, of course, it will die down to 0, and basically there'll be no probability of the particle tunneling through. But if it's a finite width barrier, there is a finite probability of the particle tunneling through, okay? Now, the way it decays also depends on the height of the potential barrier. And as you might expect, the taller the barrier, the more rapidly the wave function decays, and the tunneling probability goes down. So a taller barrier or a wider barrier causes lower tunneling probability. A shallower barrier and a thinner barrier allows the wave function to tunnel through, okay? Now, this phenomenon of tunneling, like I said, has no classical explanation at all. And it's very, very important in nature, okay, in physics. I mean, appears all over the place. So, this phenomena of radioactivity, for example, is because of tunneling of alpha particles out of the nuclei of atoms, radioactive atoms such as uranium, okay, as one example. In our class, tunneling is going to be extremely important physics and has both good aspects and bad aspects, as we'll discuss. So when you talk about MOSFETs, for example, we see that we put the gate electrode on top of a very thin gate oxide, which is an insulator, but the gate oxides are made so thin that it becomes a very narrow potential barrier for the electrons. And as a result, electrons from the channel of the MOSFET will be able to tunnel through the very, very thin gate dielectric into the gate and give rise to gate leakage currents. That turned out to be a huge problem for the semiconductor industry. And we'll discuss how people solve that by moving away from very, very thin silicon dioxide gate dielectrics to much thicker, what are called high K gate dielectrics. And that's what you have in your transistors, in your laptop, and your cell phones today, okay? Tunneling can also have some beneficial aspects. So I bet every one of you has cell phones, and I bet every one of you stores, photos and stuff like that. But that entire physics is dependent on tunneling. because what you have in your cell phone are what are called non-volatile memories, called flash memories, where you have what's called a floating gate in between the gate and the channel of a MOSFET. And the way you store information in a flash memory is you purposely tunnel electrons from the channel into this floating gate, and you trap them in a potential well between the lower dielectric and the upper dielectric. And the presence or absence of the stored electrons are your digital bits 0 and 1. Okay, so I don't want to get too much into it, but the point is tunneling is going to be very, very important. It'll be both good in some device applications and bad in other applications. Okay, so tunneling is one thing that's definitely non-classical. Okay. Oh, so I wanted to say one more thing. So this whole business of negative kinetic energies in the barrier, right? I mean, that's a very weird, funky concept, right? So how do you get around that? The way you get around that is by invoking the Heisenberg uncertainty principle. Okay. The Heisenberg uncertainty principle tells you that the uncertainty in position times uncertainty in momentum must be greater than or equal to h bar over 2. Remember that? So what Mr. Heisenberg says that, when this electron is in the barrier itself, there'll be a certain uncertainty of the order of W, okay? And then that corresponds to an uncertainty of the momentum, which should be of the order of h bar over 2W, say, right? Therefore, then the uncertainty of the kinetic energy would be that p squared or h bar squared 2W squared divided by 2m, okay? And what that tells you is when the electron appears within the barrier, there's enough quantum mechanical uncertainty of the kinetic energy, the fuzziness, that, it's a case of, don't ask, don't tell. So the electron could have an uncertainty of energy higher than this potential barrier V naught. So that's how people, philosophically wiggle out of these quandary. Okay. All right. So the final problem that we'll sketch out, solution, we won't solve it. This math is extremely complex. If you've taken a course in quantum mechanics, you'll see that the solution of electron orbiting around a nucleus, the hydrogen atom problem, or by extension, electrons in other types of atoms, is a very complicated solution, all kinds of special functions, known as spherical harmonics and things like that. So I don't want to waste time going through pages and pages of math. I just want to give you a physical sense of how the solutions are done, okay? So here, if I have electron with a charge minus q orbiting around a positive heavy proton in the hydrogen atoms there, with a radius r, we know that there'll be an electrostatic potential profile, okay? So it's a 1 over r Coulombic potential, okay? Where z is the atomic number of the atoms. In the case of hydrogen, z would be equal to 1. For other atoms, z would be whatever the atomic number is. Now, this is written in CGS units. In MKS units, that will be written as 4 pi epsilon naught r. Okay, so it's a 1 over r Coulombic potential. Okay, now this potential is, of course, spherically symmetric, right? So it doesn't matter, what the angles are of this electron orbiting around the nucleus. The only thing that matters is this radial separation r. Now, if I have a spherically symmetric potential, which depends only on the separation but doesn't depend on the angular variables, what do you think would be a smart choice of coordinates to solve the Schrodinger equation? Now it's a three-dimensional problem. Do you think the smart choice would be to use x, y, z Cartesian coordinates?
Spherical.
Spherical, very good. So you're better off using r, theta, phi spherical coordinates as shown over here, okay? So now you write down a wave function, not as a function of x, y, z. I mean, you could do that, but you're better off writing it as a function of a radial part times another function, which depends on these angular coordinates theta and phi, okay? And this special function that's a spherical part, and that's a radial part, okay? Those are known as spherical harmonics and so on and so forth, but let's not worry about that, okay? So then what you have to do is you have to solve this problem not for a particle in a rectangular potential box as before, but a particle in a 1 over r type box, okay? So that tells you then, if you go back to the solution for the rectangular box, the energies increased as n squared for a constant width L of the box, right? But now the width of the box is not constant. As I go to higher energies, the width of the box is actually increasing, right? So the L in the denominator is increasing. So as n goes up from 1 to 2, etc., the width here is smaller, the width over here is larger, and so on and so forth. And because the eigenenergies that we solved before for the particle in a box scale as n squared over L squared, what one finds is a solution of the particle in this 1 over R type box doesn't go up quadratically with n, but rather you have a separation of these energies which gradually gets closer and closer for electron in a hydrogen atom. And if you go to higher and higher energies, it'll asymptote to 0, where I've chosen my reference potential energy very far away to be the 0 of the reference energy. Okay, so if the electron comes out over here, that means that the electron has been stripped away from the hydrogen atom, and you have a hydrogen ion and a free electron. Okay, so these energies get closer and closer, and it asymptotes to the free electron in vacuum. And what Schrodinger found when he solved this Schrodinger equation for this spherically symmetric potential profile is you could reproduce exactly the energy levels that Bohr had come up with in the hydrogen atom, using his hand waving type picture and this weird assumption that the angular momentum has to be quantized in terms of n, h bar, and so on and so forth. Okay, remember the discussion from last week? Now, of course, that assumption was made a little bit more palatable by de Broglie, where he said that you can think of these electrons orbiting around this nuclei in this preferred Bohr orbits, because you have these de Broglie wavelengths, and the only allowed orbits are, there's a weird wave function. Think of it as a sort of standing wave, sine waves in this circular string. Okay, so when an integer number of these wavelengths fit within the circumference, those are the allowed orbits, and you get allowed Bohr energies. If it's a non-integer number, those are forbidden Bohr orbits. Okay. Now, what Schrodinger did was he said, these de Broglie waves are really these wave functions, psi of r and t, that have to solve in terms of the Schrodinger equation. Okay. All right. So if you solve that Schrodinger equation, which we owned, you get these expressions, and that's exactly what Bohr had come up with using his hand waving type model. This energy for the first n equal to 1, that's the lowest energy at the ground state, gives you an energy which is minus 13.6 electron volts below the vacuum level. Okay, so why is it minus? Well, I've chosen my reference of the potential energy, which is called the vacuum level, to be equal to 0. Okay, the vacuum level means if I pull the electron away, strip the electron away from the attractive forces of the positive nucleus and move it very, very far away where it's not seeing any attractive forces anymore, I choose that potential energy reference and I call that the vacuum level. Okay, and that's what we'll be doing in our class also. So the reference potential energy will be when you take the electron out of the transistor or diode or whatever, move it very, very far away from the influence of any other objects, and you set that potential energy as your reference potential. Now, with respect to that, a bound electron would obviously have a negative energy, right? Because it's bound in a potential well. That's why the ground state has a minus sign, minus 13.6 electron volts. By the way, the term electron volt, that unit, is a very common unit of energy that we'll be using. And it basically is the energy that electron would gain if it moves through a potential step of 1 volt. Yes, so electron moving through a potential step of 1 volt has an energy of 1 electron volt. On the other hand, if the battery had a voltage of, say, 4 volts, that would have an energy of 4 electron volts. Okay, so that's why people like this units of electron volts. It's whatever the voltage is, it's that many electron volts of energy. Okay, now to convert that to MKS units, you have to multiply the voltage by the charge of the electron, where the charge of the electron is 1.6 times 10 to the power minus 19 coulombs. So that gives you the energy in joules. Okay, and when you actually work out numbers, you very often have to convert that to joules by multiplying electron volt units by the charge of the electron. But in most cases, don't have to worry about that. You can stay within electron volt units. And I like that because whatever the voltage is in the problem, the electron gains that many electron volts of energy. The N over here are your quantum numbers that Bohr had introduced, but now you'll see that you have 4 different quantum numbers you have to worry about in the Schrodinger derivation, where these Bohr values of N are now called the principal quantum number, okay? And these are essentially what determines these energies in a broad sense, okay? Now we'll see more details in just a second that hopefully you'll recall from your chemistry classes, okay? Now, when you talked about the particle in a box, remember we said that the reason we have these distinct eigenstates and different eigenenergies for n equal to 1, n equal to 2, and so on and so forth, is really, if you think about it, ultimately determined by the boundary conditions. In this case, the boundary conditions where psi of 0 and psi of L have to vanish, right? So anytime you impose boundary conditions on the wave function, you introduce quantization effects as shown over here. Well, what are the boundary conditions for this? Well, the boundary conditions are whatever wave functions that I'll get, okay, have to vanish at infinity, okay? And although I'm not going to go into the detailed analysis of that, I'm just telling you that that's the boundary condition that's imposed, that the wave function has to vanish at infinity. And when you put that boundary condition, you end up with these discrete quantum numbers, okay, the so-called principal quantum numbers, okay? Now, we're not done though. As I said, there are 3 other quantum numbers that pop up in atomic physics or in chemistry that hopefully you'll recall. And that is for every value of n, this principal quantum number, n can be 1, 2, 3, and so on and so forth, you can have what are called the orbital angular momentum quantum numbers, L, which can range between 0, 1, all the way up to n minus 1. So if I have, say, a Bohr orbit n equal to 3, the values of L would be 0, 1, and 2. Now, what is the physical interpretation of L? The physical interpretation is if L equals 0, those are like your circular Bohr orbits. So that's L equal to 0. In chemistry, those are sometimes called the S-type subshells, okay? L equal to 1 is a more elliptical Bohr orbit. L equal to 1, those are called the P-type subshells, okay? Similarly, L equal to 2, it's more elliptical and so on and so forth, okay? Now, what one finds is these energies for these different subshells for a particular value of n are going to be very close together, but in general, higher the value of L, the more it'll be slightly higher up in energy because it's flying farther away from this positive nucleus, right? So there'll be some differences between L equal to 0 and L equal to 1, but they'll be kind of closely spaced together. On the other hand, for n equal to 1 versus n equal to 2, that separation will be much larger, okay? While within the n equal to 2, say 2s and 2p, that separation will be a little bit smaller, typically. You can go on, and the next one is called D, and so on and so forth. And the reason you have these weird symbols is when people started doing these experiments, they looked at these sharp spectral lines for excited atoms, as we discussed last week. And they said, the first set of transitions look very sharp to my eye. So those were called the S-type subshells. The next one, not quite as sharp, but it's still pretty bright, principal. Next one is a little bit fuzzy, diffuse, F. And then they said, we're running out of ideas. After that, we'll just go alphabetically, SP, F. You just go alphabetically after that, okay? But for most cases, you really only will be dealing with the S and the P subshells in this class. If you have other more complicated so-called rare earth elements, sometimes you'll have D and F. You generally don't have to go beyond that anyways. All right, so then the third quantum number is the so-called magnetic quantum number, okay? And the physical interpretation of that is when the electron orbits around the nucleus, it's like a tiny circulating electric current, okay, which has a magnetic moment associated with that. So now if I impose an external magnetic field B, these tiny elemental magnets can line up entirely with that external magnetic field or can have discrete orientations with respect to that external magnetic field. And those discrete orientations of these elemental atomic magnets correspond to values of M ranging from plus L, when it's totally lined up, L minus 1, that's L equal to M equal to 0, all the way up to M equal to minus L. Okay, so M ranges from L minus 1, 0, all the way up to minus L. So how many values of M do I have then? I'll have 2L plus 1 possible values of M. Okay. And then finally, the fourth quantum number, and that's the strangest of all, it's a purely quantum mechanical concept, is called the spin quantum number. Okay. So here, I'm giving you a picture which is not strictly accurate, but good enough for our purposes. So you can think of this electron as a sphere which is spinning rapidly around its own axis. Okay. And depending on whether it's spinning clockwise or anti-clockwise, that spinning charge also has a magnetic moment, and that can line up either along the magnetic field or opposite to the electric field. Okay. And the magnitude of that magnetic moment in appropriate units of that are used to measure this M values of the magnetic moment, this is called the orbital angular quantum number. In those units, these happen to have a value of either plus or minus half. Okay. The magnitudes are given by plus minus half times h bar. Okay. So the reduced Planck constant is in what the dimensions of these magnetic moments are. Okay. I'm just stating all of this, of course, right? And I haven't proved any of this. If you're curious and if you haven't taken a course in quantum mechanics, you can just pick up any undergrad textbook on quantum mechanics, such as Griffith, and goes through all those derivations. But I'll warn you, it's really page after really complicated, special functions, logarithm polynomials, and spherical harmonics, and pretty soon, and I get lost. So for our purposes, we don't need to really worry about that. Okay. All right. So the upshot is now, unlike the Bohr model where you had a single quantum number n, now you have 4 quantum numbers to deal with, which are subject to these rules. And that really is used to explain a lot of chemistry and a lot of semiconductor physics. So I'm pretty sure you've seen some of this in your AP chemistry classes in high school or freshman chemistry and things like that. All right, so let's sketch these out and see what the possible values of these quantum numbers are and the corresponding energies. As I said, n equal to 1 to n equal to 2, huge change in energy. But within that second shell, 2s and 2p will be very close together. The 2p will be slightly higher up in energy, and so on and so forth. Okay. Now, how many possible values of these wave functions can I have? The single particle wave functions in chemistry are also called orbitals. Okay. So for n equal to 1, the only possible value of L is 0, right? Because remember, L ranges from 0 to n minus 1. If L equals 0, M can only be equal to 0 because M ranges from minus to plus L. Okay. But then you can have spin half or spin minus half. So the first subshell or first shell can have 2 states in it. Okay. It has 1 orbital, but then the number of states will be times 2, spin half and spin minus half. Okay. So you can go along the lines and you see what the possible values of the orbitals are. So for the S-type subshells, you have 2. For P, you have possible 6. Okay. Because now P equals 1 means M can be minus 1, 0, 1, and each of those can be spin half or minus half, and so on and so forth. Okay. So if you count the total number of electrons that can fit into the shells, it ranges as 2, 8, etc., etc. So it basically ranges as 2n squared. So n equal to 1, n equal to 2 gives you the 2 for the 2s plus 6 for that, for the p-type subshells. So n equal to 2 squared is 4 times 2, 8. Next one would be 18, and so on and so forth. Okay. Hopefully you remember that from your chemistry classes. All right. The only other thing that hopefully you also remember is when you put electrons into these various quantum states, so these are like your standing wave patterns of your de Broglie waves, if you will, you have to impose one more condition in physics. Does anyone remember what that condition is? What principle?
Is it Pauli's exclusion principle?
Excellent, excellent. You get an A in the class. So you can't put more than one electron into a quantum state, okay? That's a property of spin half particles, which are also called fermions after Enrico Fermi, okay? I'll get into this in chapter 3 in more detail. where we'll see you have two types of particles in nature, spin half particles or integer spin particles, which are known as bosons, after an Indian physicist called Satyan Bose. All right, let's look at the shapes of these wave functions, the spatial dependencies, and specifically the wave function magnitude squared, because that's what gives you the probability density function, okay? So once again, if you solve for the solution, what you'll find is for the S-type orbitals, which correspond to L equal to 0, okay, you end up getting spherically symmetric wave functions and wave function magnitude squared. There's only a radial dependency of the form e to the power minus some constant times r. Now for hydrogen, the atomic number is 1. So it's basically e to the power minus r over a naught, where a naught is your Bohr radius of half an angstrom, okay? For other atoms, of course, z would be other numbers, okay? So there's no theta and phi dependency, okay? So the wave function magnitude squared, if you plot it out in space, will be the spherically symmetric shapes, okay? Equally likely to be found everywhere. For the n equal to 2, once again, spherically symmetric, but now you have multiple lobes. So you're likely to find the particle near the nucleus, okay? But also likely to find it at that distance, okay? So that corresponds to your second Bohr radius, okay? But not in between, because here you have a 0. So those are the standing wave patterns that I talked about before in the particle in a box state also, okay? Now, what you'll find is to get the actual probability as a function of radius, you have to integrate out in terms of these shells, okay, where the thickness of the shells would be given by 4 pi r squared dr. So that's the thickness of the shell. So when you weight it out by the thickness of the shells, you'll find that the electron would orbit in the second Bohr orbit. Similarly, this is the third Bohr orbit, and so on and so forth. Okay, these are the spherically symmetric shells. Now, at this point, one needs to point out sort of an error in the physical picture that the Bohr model tells you. Okay, so in the Bohr model, you think of these electrons orbiting around this nucleus, right? And clearly that has an angular momentum. But on the other hand, for this S-type shells, remember we said that the angular momentum L equal to 0, right? So in the quantum mechanical picture, although Bohr seems to tell you that the electrons are orbiting in this nice, precise orbits, in the quantum mechanical picture, there's the fuzziness. So you don't know exactly where the electron is. And actually in the spherical shells, the angular momentum of this electron is 0. On the other hand, in the P-type shells, subshells, you'll have a non-zero angular momentum. So the P-type, that's a more complicated case, okay? So once again, by solving the Schrodinger equation, you'll find that you have this exponential dependency where I'm writing sigma as r divided by a naught times r. So now this r parameter over here. And now you start seeing angular dependency. So cosine theta, also phi, and so on and so forth, okay? You take the square of these wave functions. So for these P-type orbitals, you'll find that the px orbitals have two lobes. You have a positive amplitude and a negative amplitude pointing along the x-axis. Py, positive amplitude, negative amplitude along the y-axis, and so on and so forth, okay? Now, if these are the wave functions, what would the probabilities look like? The probability would peak in the positive x direction, but would the probability be negative in the negative x direction? How is probability density related to the wave function?
It's the magnitude squared.
Right. So although the wave function may have a positive and a negative lobe, once you squared them, it's going to be positive along this direction or this direction. So you have this chemical bond which points along the x-axis here. In the PUI case, it points along the y-axis and z-axis and so on and so forth. Okay.
What does the sigma mean in that equation?
Sigma is just proportional to the radius. So I define sigma as r, radial distance, normalized with respect to the
right.
radius.
Sorry, I missed that.
Yeah. All right. So that brings us to the famous periodic table of Mendeleev, okay, where I guess in the next class, we'll start building up the electronic structure of atoms according to these rules of quantum mechanics that I've just said, starting with hydrogen, where the one electron gets put into the first shell, helium, the second electron spin up, spin down, so it will still fade. But then by the time I come to lithium, there's no more room for it. That would make Mr. Pauli very, very upset. So that has to be put into the second shell, n equal to 2, and so on and so forth. Okay, you keep going, and as you keep going, at some point you fill up all the available states, and whenever you do, you have what is called a closed shell, and those correspond to the so-called noble gases such as neon or helium or argon, and so on and so forth. Okay, now you may remember from your chemistry classes that atoms like to have an outermost shell, the so-called valence shell, which is complete or closed. All the states that are available are occupied, and if they're occupied, those atoms don't need to form chemical bonds with any other elements. That's why they're called the noble gases. Okay, they call them noble gases because in ancient times, nobles are very hoity-toity, and they would not interact with us commoners. So similarly, this noble gases, they're very proud. They don't want to enter into chemical reactions with other elements. Okay, so what you'll see in the next class is our fun starts with an element such as silicon, which is an atomic number of 14. So I have 14 protons in the nucleus and 14 electrons. The first 10 of those have the same structure as neon. Okay, and see that has no particular relevance for semiconductors. All the fun starts with the outermost valence shell, 3s2, 3p2. But of course, in the p subshell, we have room for 6. So 2 plus 6, room for 8, but only 4 of those are occupied. So now I have an incomplete shell in the case of silicon, which makes it reactive and also very, very interesting for semiconductor physics. So that's where we'll start off in the next class. Any questions? All right, see you.
Thank you, Professor.